So now let's continue with the second part of our lectures. So for this part, we shall be studying enzyme kinetics and inhibition. So the topics for this are shown here. So we shall be discussing first the concept of rates and reaction rates as well as kinetics, which we shall be applying both in Michaelis-Menten as well as Lineweaver-Burk graph. And then we'll end the lecture with enzyme inhibition. So the learning objectives are shown here. So first of all, what is rate? Well, we can define rate as a measure of change over a period of time. So the synonyms for rate are speed and velocity. So in this example, we have a truck that travels a distance of 10 meters and it took about 5 seconds for the truck to traverse that distance. So the rate, the speed, the velocity for the truck is 2 meters per second. So let's apply this concept of rate to a reaction. So the question is, what is a reaction rate? So we did say that rate is a measure of change over a period of time. So if we apply this to a reaction, we can say that the change can be measured in terms of formation of products over a period of time. So this is expressed in the formula change in the concentration of product over change in time. Say for example, we have here a 1 ml test tube and contained within it are the yellow particles, which stands for the reactant. Let's see how many products will be formed after a given time. So the concentration of products that will be formed at a given time corresponds to the reaction rate. So we have here 10 particles of products were produced in 10 seconds. So we can say that the reaction rate is 10 particle per ml per 10 seconds, or the reaction rate is 1 particle per ml per second. So there are actually two relationships between the reactant concentration and reaction velocity. So we have here on your left the illustration for what is known as a zero order kinetics, whereas on your right of the screen depicts the first order kinetics. So in zero order kinetics, the reactant concentration is independent, the reaction velocity is independent of reactant concentration. So it doesn't matter whether you have a lot or very little reactant, the reaction rate or V naught remains the same. On the other hand, on the right side of your screen, you have a first order kinetics wherein the reaction rate or V naught depends on the concentration of reactant. More reactant means a faster reaction rate. So this is of course true for uncatalyzed reactions. Some reactions obey first order and there are those that obey zero order. So what about for enzyme catalyzed reaction? So let's move on to an enzyme catalyzed reaction. Which of the two do you think obeys an enzyme catalyzed reaction? Is it choice A, zero order exclusively, or choice B, first order exclusively? Well, the answer is actually neither, as both reaction orders are present in enzyme catalyzed reaction as depicted by the Michaelis-Menten curve. So in Michaelis-Menten curve, on the x-axis we have the substrate concentration, whereas on the y-axis we have the reaction velocity or V naught, and what we have here is a hyperbolic curve. So initially, when the substrate concentration is very low, it is almost like a straight line going up. So we say that the reaction obeys first order kinetics. On the other hand, when the substrate concentration is very high, it's a flat line that is constant. So it's now obeying zero order kinetics. And in between, there is a transition we call the mixed order kinetics. So the question is, why does it obey first order kinetics initially and then eventually transitions to zero-order kinetics when the substrate concentration is very high. So in order for us to understand that, let's construct a Michaelis-Menten curve. So in this particular example, we have the boxes representing enzymes, and then we shall be introducing different concentrations of substrate starting from very low and eventually increasing it, and then we shall measure the corresponding reaction velocity as represented by the enzyme substrate concentration. So with just one substrate, after a given time, there would be one product form. So let's put that one substrate, one product form. So now let's start on a clean slate. Let's slowly increase the amount of substrates that will be introduced. So after a given time, after the two substrates have been introduced, two products have been formed. So let's put it in there, 2 for the reaction velocity. And then starting again on a clean slate, let's introduce more substrate, 5 substrates. After a given time, there are 5 products formed. So again, let's start on a clean slate and slowly increase the amount of substrates. So this time, let's introduce 10 substrates. With 10 substrates, we expect to produce more products, 10 products. So at this point, you will see that there seems to be a linear direct relationship between the substrate concentration and the corresponding product or reaction velocity. So this seems to obey first order kinetics. Now let's introduce more substrate now, 20. All binding sites are occupied and we produce 20 products after a given time. So let's double the amount of substrate to 40, starting on a clean slate. So even if we increase the substrate concentration, the amount of products produced remains stuck at 20. Maybe if we introduce 60 substrates, we can go beyond 20 products. So as expected, the amount of products remains constant at 20. So now we see that the reaction velocity is obeying zero order kinetics. So if we're going to plot our result, so initially, when the substrate concentration is very low, it's like straight line going up. Whereas when the substrate concentration is very high, it's a flat line. So the best curve that fits this particular trend is a hyperbolic curve. So just to recap, initially, an enzyme catalyzed reaction obeys first order kinetics. And the reason for that is that there are more enzymes than there are substrates. So if we introduce more substrates, more enzyme binding sites will be occupied, and consequently more products will be formed, corresponding to a faster reaction rate. Now if we keep on introducing more substrate, there will come a point wherein all enzyme binding sites will be occupied. So the enzyme is said to be saturated, and no matter how much substrate we add, the amount of products that will be formed remains constant. It now obeys zero order kinetics. So let's recap. In an enzyme catalyzed reaction at low substrate concentration, the reaction obeys first order kinetics. The reason? There are more enzymes than there are substrate. And addition of more substrate increases the reaction rate V0. The reason, all substrates are being converted into products. At high substrate concentration, enzyme catalyzed reaction now obeys zero-order kinetics. All active sites are occupied, and enzyme is saturated. Now the reaction rate has reached its maximum. We call it the Vmax. So at Vmax, further addition of substrate cannot increase the rate beyond the Vmax. So this is the illustration of the Vmax. It corresponds to the point that is shown on the y-axis. So in our example, the Vmax is 20. Of course, half of 20 is 10. We call 10 the Vmax 1/2. Now this Vmax 1/2 corresponds to a particular substrate concentration called Km, or the Michaelis constant. So Michaelis constant, or Km, can be defined as the substrate concentration that will produce Vmax 1/2. Another way to view it is that it's the substrate concentration that will fill up half of the total enzyme binding sites. The Km is an important number because it's a measure of how well a substrate complexes with an enzyme. In other words, it's a measure of binding affinity. A low Km means high binding affinity, and vice versa. So in this example, we have two curves, blue and green, with their corresponding Km. The blue curve has a relatively lower Km, whereas the green curve has a relatively higher Km. The blue curve has a lower Km, and if you take a look at the slope, it reaches the Vmax easily, which means the enzyme is easily saturated. On the other hand, the green curve has a higher Km, and it takes a lot of substrate to saturate the enzyme. So that means that the enzyme has low binding affinity to the substrate. So a high Km means low binding affinity, and vice versa would be true. Now, if you take a look at the Michaelis-Menten equation, it describes the relationship between substrate concentration versus reaction velocity. And this relationship is nonlinear hyperbolic. And the problem with this is that the Km is difficult to estimate or extrapolate. Now, the solution is to convert Michaelis-Menten equation into its derivative called the Lineweaver-Burk equation. So this is simply the reciprocal of the Michaelis-Menten. So when you graph it, it's now 1 over S versus 1 over V naught. And the relationship between the two is linear. And because the relationship is linear, Km and Vmax are easily extrapolated. So how do we convert now Michaelis-Menten equation into the Lineweaver-Burk formula? It's actually very simple. We simply obtain the reciprocal of the Michaelis-Menten equation. Once we have obtained the reciprocal, we separate Km from S. Now, if you notice, Km and S have a common denominator, and this is the Vmax over multiplied by substrate concentration. So this is the resulting equation. The next step is to cancel and simplify. What can we cancel here? That would be the S. So the final formula is shown here. If you notice, it follows a certain algebraic format. Y is equal to mx plus b, where y is the 1 over v naught. The b is the y-intercept, it's 1 over vmax, whereas the x is 1 over s, with the slope m corresponding to km over vmax. So if we're going to plot this now, instead of a hyperbolic curve, what you have is a linear line. Now let's apply this to a particular problem in order for you to appreciate the Michaelis-Menten as well as the Lineweaver-Burk. Say you want to determine the Vmax and Km for a particular enzyme. So you can do this by measuring the reaction rate V0 at different substrate concentration S, just like what we did in our earlier experiment. Now, this resulted to a data that is shown on the right side of the screen. So if we're going to plot this now, substrate concentration versus reaction velocity, this would be our result. And the line that fits this is a hyperbolic curve. So this is called the Michaelis-Menten curve. So what is our Vmax now? Now it seems like somewhere around 35 is our Vmax. But we're not really sure because if we add more substrate, there are two possibilities. The value can go up beyond 35 or it can remain at 35. If it does remain at 35, then 35 is our Vmax, whereas if it continues to rise, then 35 is not our Vmax. Since it would be impossible to pinpoint the Vmax, it would be impossible as well to determine what Vmax 1/2 is, and this also makes determination of the Km difficult. So the solution is to convert everything into its reciprocal form. So the S becomes 1 over S, the V0 becomes 1 over V0. So if we plot this now, what we get are 3 points that perfectly align each other. So it's a linear graph. Extrapolate the 3 points until it intersects with the y-axis. Why particularly this y-axis? This will give you 1 over Vmax. So if you obtain the reciprocal of 0.02, that will give you now the Vmax. Extrapolate some more until it intersects with the x-axis. This will give you the reciprocal of 1 over Km. Just disregard the negative sign. So to recap, in Michaelis-Menten, we take a look at the relationship between substrate concentration versus reaction velocity V0 in an enzyme catalyzed reaction. The relationship is hyperbolic, whereas its derivative, the Lineweaver-Burk, is the reciprocal relationship between substrate concentration versus reaction velocity, or 1 over S versus 1 over V0. And this relationship is linear. So now let's apply this to enzyme inhibition. Now, based on the affinity of the inhibitor, enzyme inhibitors can either be irreversible or reversible, and if it covalently binds to the enzyme, this is classified as irreversible, whereas if it's a non-covalent binding, then this is reversible enzyme inhibition. The mechanism can be either competitive or non-competitive. So we'll just concentrate on reversible enzyme inhibition. Let's start first with competitive enzyme inhibition, wherein the Vmax is unchanged and then the Km increases. So in reversible competitive enzyme inhibition, the substrate and inhibitor are competing for the active site. If the substrate is the one that binds to the enzyme's active site, products can be formed. However, if the active site is blocked by the inhibitor, there shall be no ES complex formed and no products can be formed. So to recap, in reversible competitive inhibition, substrate and inhibitor are competing for the active site. Inhibitors block the active site. Now, the reason for this is that the inhibitors are often structural analogs of substrate. So the question is, how is competitive inhibition overcome? Let's take a look at this example. Let's say the substrate and inhibitor have equal affinity for the active site. Who has a greater chance of binding? That would be equal. But if we increase the amount of substrate, there's a greater chance of forming the ES complex and products can be formed, rendering the inhibitor insignificant. So if you graph this, the green line without the inhibitor and the red line in the presence of the inhibitor, in the presence of the inhibitor, we can still reach the original Vmax, but it will take a lot of substrate. So we say that the Vmax is unchanged, but if you notice, the Km is apparently increased in the presence of the competitive inhibitor. So to recap, the Vmax may be attained at a higher substrate concentration, so we say that the Vmax is unchanged. However, the Km is apparently increased. Now, what is the reason why the Km is increased? Now, let's define Km as for this lecture, we can define or visualize the Km as the amount of substrate that will fill up half of the enzyme. So in this example, only 2 substrate are needed to fill up half of the enzyme. So we have a Km of 2 without the inhibitor. Now let's introduce a competitive inhibitor. Now, in the presence of the competitive inhibitor, the 2 substrates are no longer sufficient to fill up half of the enzyme binding sites. So the Km must be higher than or greater than 2, probably 5 in this example. So it takes about 5 substrate to fill up half of the enzyme binding sites. So the Km is apparently increased. So let's move on now to reversible competitive inhibition. So the substrate and inhibitor have different binding site, and that would be the allosteric site. So the inhibitor can either bind first or can bind after the substrate is bound to the active site. So the result is an EIS complex that is inactive, and therefore products cannot be formed. So inhibitors can bind to the enzyme at the same time as a substrate. So the inhibitors bind to allosteric site and not the active site. So the resulting EIS and EI complexes are inactive. So what if we increase the substrate concentration? Will this overcome the inhibitor? So in this illustration, there are several substrates and just one inhibitor. And no matter how much substrate there are, we still form the EIS complex, which is inactive, and therefore no products can be formed. So if we graph this, the red line representing the presence of enzyme inhibitor, no matter how much substrate is added, we can no longer attain the original Vmax. So we say that the Vmax is decreased in the presence of the inhibitor. However, the Km is unchanged. So to recap, the Vmax cannot be attained even at a higher substrate concentration. So we say that the Vmax is decreased, whereas the Km is unchanged. So the question is, why is the Km unchanged? So we did define the Km as the amount of substrate that can fill up half of the enzyme binding sites, active site. So in this example, we have a Km of 2. Now let's introduce an inhibitor that binds to the allosteric site. So even in the presence of the inhibitor, the original 2 substrates are still capable of binding to the enzyme, so the Km is unchanged. So what if you use now the Lineweaver-Burk plot to depict competitive versus non-competitive? Red line represents the presence of inhibitor. In competitive inhibition, you will see that the red and the red and the green lines have a common y-intercept, which means that the Vmax is unchanged. On the other hand, on the right side of your screen, you have the non-competitive inhibition, wherein the red line and the green line have a common x-intercept, which means that the Km is unchanged. So in competitive inhibition, without the inhibitor and in the presence of the inhibitor, both lines have a common y-intercept, which means that the Vmax is unchanged. On the other hand, in non-competitive, those two lines have a common y-intercept, which means that let me correct. Those two lines have a common x-intercept, which means that the Km is unchanged. So it can be summarized by this tabulation. In competitive inhibition, the inhibitor binds to the active site. There's no change in the Vmax, and the Km is apparently increased. On the other hand, in non-competitive inhibition, the inhibitor binds to the allosteric site, resulting to a reduction in Vmax, but the Km is unchanged. So in summary, there are two types of inhibition based on mechanism, competitive versus non-competitive, and the type of enzyme inhibition can be determined based on the changes on either Vmax and Km, which can be discerned on either Michaelis-Menten and Lineweaver-Burk graphs.